It is a pleasure to be here, and an honor, really. And yes, I have these two different worlds that I straddle between the publishing world and this popular science or mathematics. Let's see, you can hear me fine if I do that, right?
Yep.
That way I can almost see some of you. This is great. Thank you so much. I want to thank you for coming out tonight so that we can talk about the topic of my new book, which is 50 Shades of Grey. Oh, sorry, not that 50 Shades, these 50 Shades of Grey. And of course, not just 50 Shades, of course, but thousands of shades, or millions of shades, really, and not just gray, but color and size, time, heat, all kinds of things that I call spectrums. So some people call them continua, some people call them ranges, but I call them spectrums. And you get a spectrum whenever you start to compare two or more things, right? So, for example, this yellow is brighter than that yellow. So you can compare things. And humans love comparing things, because this is how we make sense of the world around us. You compare this rock to that rock, and this rock is harder, this rock is more valuable. We make comparisons, and that's where our sense of meaning, in large part, comes from. We particularly love the extremes of spectrums. Have you noticed that? Always all the way off to the edge. So this guy is not just faster than these other guys. This guy is the fastest human on Earth, Usain Bolt. We love that. This is not just a hot place. This is the hottest place on Earth. This is Death Valley in California. Some of you actually may have heard that there's this little town in Libya that was supposed to be the hottest place on Earth, for those of you who love going through Guinness Book of World Records. This town in Libya actually was, for the past 100 years, the hottest place on Earth, and then a bunch of historians went back and looked at the records, and they said, something's wrong here, and they figured out that the measurements were incorrect, and so they stripped Libya from the hottest place on Earth record books, and they gave it to Death Valley. So there you go. But how hot was it in Death Valley in 1913? So in order to communicate a sense of scale, whatever scale you want, you need to build some sort of scale with numbers on it, right? So for example, with temperature, let's just take temperature to start with. Let's say, hypothetically, that water freezes at 0 and boils at 100. That's a pretty good scale. That is the scale that Anders Celsius came up with in 1742. Actually, that's not entirely true. Celsius actually said, let's make boiling at 0 and freezing at 100. Which made absolutely no sense to anybody around him, but he was insistent on the point. Fortunately, a few years later, he died, and everyone got together and agreed to flip it around. So, just true story. So let's say, hypothetically, that freezing is going to be at 0 and boiling is going to be at 100. Okay? So that's good. So if you have that scale, then each degree on that scale is going to be 1/100th of a step. So we call it a degree centigrade. Centigrade is Latin for 100 steps. So they called it degrees centigrade. Last century, in the 20th century, a bunch of scientists got together again, and they said, okay, let's forget the centigrade part, let's call it Celsius. And of course, the Celsius scale is what pretty much everybody on planet Earth uses to describe temperature, except of course us in America, where we're stuck with Fahrenheit, which is fine. Fahrenheit is adequate, but Fahrenheit describes the same thing. It describes temperature, but with different numbers. Now, random fact, and you have to understand something. I love random facts, little weird facts. It's one of my things. And if you look at Joy of Pi, you look at the Flying Book, or at Spectrums, you'll see I have lots of marginalia, all the little quotes and sidebars and so on that have little facts. So you sort of pick it up, and everywhere you look, you're like, oh, that's interesting. So, random weird fact. The Celsius scale and the Fahrenheit scale for any given temperature gives a different number, right? You always have a different number, except at one point. There's one point where they converge, and that is minus 40 degrees. So now you know. Now you know. Next time you're on Spectrum's Jeopardy, you'll know that minus 40 degrees is where they converge to one place. So So this is a pretty clear spectrum from cold to hot. Now this is one of the 6 spectrums that I talk about in my book, Spectrums, Our Mind-Boggling Universe from Infinitesimal to Infinity. And in each chapter, I look at a spectrum. So whether it's heat or time or size or whatever, and I look at how it's defined, I look at how we experience it, what is the normal range of that spectrum, like with temperature, what's the normal range of temperature here on planet Earth, and then I push it further. I try and go further with it, and I look at the extremes. So, for example, what happens to the air around us if it gets so cold that the gas turns to liquid and then solid, if it actually freezes, right? So everything freezes if you get it cold enough, right? So oxygen freezes at 223 degrees below 0 Celsius. This is actually not oxygen, this is carbon dioxide frozen, but you get the idea. It's an ice, it's an icy thing. And it is, this is what we call dry ice, frozen carbon dioxide. But at minus 223 degrees Celsius, oxygen will freeze to a solid. Okay, so what's going on there? The molecules in oxygen, or nitrogen, carbon dioxide, whatever, the molecules are going to start slowing down, right? In a gas, they're all over the place. Here in this room, the air moving around us, the air molecules are actually moving around at over 1,100 miles an hour. Little tiny, it doesn't go very far, but it moving around at over 1,100 miles an hour, okay? And that is actually pushing up. The reason it's moving so fast is it is at this temperature. Temperature determines speed of those molecules, and it's buzzing against your skin, and they're bouncing up against each other's magnetic fields, and they're transferring energy, they're transferring sound, which we'll talk about in just a little bit, and the air around us is moving around a lot. And you cool it down, and everything's going to get slower, right? But things never stop entirely. Even when it crystallizes, even when water crystallizes to ice or air crystallizes into that, it's going to still be moving a little bit. The molecules never stop moving. Important point. They never stop moving, even right along their little internal axes of freedom. They're like moving around, buzzing around, almost like a nervous tick, constantly moving, okay? And that's interesting because it explains why sometimes you get this kind of unexpected behavior. Everything, even when it's a solid, because it's still moving, sometimes goes through a phase change. A phase change, for example, is you have a block of ice, and on the edge of that ice, it's going to suddenly, some of the molecules are going to suddenly become liquid, and then they'll freeze back again. Or they'll skip the liquid entirely, and they'll literally boil off the surface in a phase change called sublimation. And you've all experienced this if you have a freezer. You open you put some ice in the freezer, and you open it up 2 months later, and you realize the ice has gotten smaller. And you keep the ice there for a long enough time, and it disappears. It literally has boiled off inside the freezer, even though you've kept it freezing. It's boiled off because you constantly have this motion going on under the hood. Now, as I said, it's a fundamental law of physics. There's always motion, even in deep space. Way out in deep space, you figure that's probably the coldest place in the universe. It's not, but in deep space, there is always a little bit of motion. There's enough interstellar gas, there's enough radiation out there that it's usually about, it's cold, it's minus 270 degrees Celsius. So, but deep space, just sort of like in between galaxies, is not the coldest place. This place, as far as we know, is the coldest place that we found in space so far. This is called the Boomerang Nebula, and the Boomerang Nebula is about 5,000 light years away. It's in the constellation Centaurus, and it's a nebula. It's from an exploding star. There was a supernova, star exploded. You'd think that would mean it's very, very hot. Typically, it's going to be very hot. But in this case, something interesting happened. There was this huge amount of gas, and it's being sent out in all directions very quickly. Now, you've held a spray can, aerosol can, and you've started spraying, right? And what happens to the can when you let out the gas? The gas expands very quickly. It becomes very, very cold. And that's what's happening here. The gas is expanding through space so fast that the ambient temperature in space has actually dropped lower than the rest of deep space around it, which I find fascinating. To me, this kind of thing is bizarrely fascinating. Like, really? How could that happen? But it's true. So, now, a spectrum, the spectrum of cold, has to have an end point. It has to have a hard stop at cold. Why? Because, as I mentioned, the temperature relates to how fast things are going to be moving. And fundamental law of physics, things can't stop moving. So you get it colder and colder and colder, and the molecules start freezing up, and then the atoms themselves start moving slower. The electrons and subatomic particles start moving slower, but you cannot stop them. If you did, theoretically, you would break what's called the Heisenberg uncertainty principle. Cannot do that, because that says that we could actually pinpoint exactly where an electron was at any given point. Not allowed to do that. It has to always be a mystery. It's something I talk about in the book. Whole issue of mystery, but that's going to go off on a different tangent. So there has to be a point at the bottom of your temperature spectrum at which point you cannot go any farther. And that point is called absolute zero. And that is at minus 273.16 degrees Celsius, or at this point we start talking about a different scale, a third scale, the Kelvin scale, and absolute zero is 0 Kelvin. So it's easy as that. Now, interesting, kind of. I talk about a lot of interesting things that happen down at that low, near absolute zero. It turns out issues with supercooled fluids and so on, very intriguing. But what I find intriguing is not just to look at one end of the spectrum, but what about the other end of the spectrum? Because if there's an absolute zero, is there an absolute hot? Which it's kind of an interesting thing. People don't usually think about that. But is there an absolute hot? Well, when you get stuff warm, it turns to a gas, right? And when you get gas really hot, it turns into a plasma. And plasma is actually what most of the stuff, most of the atoms in our universe are. It's plasma. Plasma is when atoms get so hot, not only do they break apart from their molecules, but they get so hot that they start shaking off electrons, and they become ionized. They're charged. And this is, again, what most of the stuff in interstellar gas is plasma. The stuff inside stars, like our sun here, is plasma. I don't know if you can see the date stamp at the bottom of here. I love the fact this was 2 days ago. The fact that you can go on the internet and get a photograph of what the sun looked like 2 days ago at 5 o'clock. I love that. Anyway, so this is plasma. So plasma is great. And inside the sun, by the way, inside our sun, it's about 15 million degrees Celsius, which is about 27 million degrees Fahrenheit. So that's pretty hot. When a sun gets very old, it sometimes explodes, called a supernova, right? Or nova, or really big one is supernova. At that point, it could become thousands of times hotter, into the billions of degrees. Billions is 9 zeros. So that's even hotter. However, here on Earth, we can make things even hotter. So at the Large Hadron Collider outside of Geneva, it's actually the little Alice thing attached to the LHC, they have recently, in fact this year, 2012, broken the record for the hottest point ever, the hottest material ever. They've smashed, I believe it was lead icons into each other, it might have been gold, into each other, and they've created a little area that they believe to be 6 trillion degrees. So that's 6 with 12 zeros. That's 6,000 billion degrees. Okay? So at this temperature, something interesting happens. At this temperature, the atoms, the plasma atoms, actually shake so much that they literally melt. And they melt into subatomic particles called, I'm not making this up, a quark-gluon soup. That's what they call it. It's a soup. It's a sort of a slightly viscous nature of the quarks and subatomic particles in this soup. Now, why would they care? Why would they want to do this? Well, this is about what the universe was like, they think, a few milliseconds after the Big Bang. So when you're trying to figure out how did our universe come to be like this, you want to go back to the beginning. just like obsessive psychotherapists, psychoanalysts, go back to the beginning, all the way back to the beginning. What happened in that early few milliseconds? Well, we want to know what a quark gluon soup is like. And how did it even get that? So that's very, very, very hot, I guess is what you'd call that. But it's still not the hottest that it could be. There is a theoretical upper limit to the temperature scale. And here's why. As I keep saying, the hotter it gets, the faster things are going to move around. Those little particles are going to move around, right? So at some point, they're going to start approaching the speed of light. They're going so fast. And as we all know, speed of light is another one of those hard stops. Asymptotic limit, you cannot get past that. So those little particles are moving so fast that they're nearing the speed of light. And Einstein figured out that as objects get faster, especially near the speed of light, they get denser. You might say heavier. So as those little particles move toward the speed of light, they get so dense that at some point they turn into their own little black hole, which would be bad, I guess. Cannot go beyond that. So that point, German physicist Max Planck figured out that that point happens at 1.4 times 10 to the 32 degrees Kelvin. Or Celsius, because at that point it doesn't really matter. Celsius, Kelvin. It's a lot. So this is 1.4 with 32 zeros, which is literally 140,000 million billion trillion degrees. That is, if you work it out. And that's what I do. That's what I've spent the past 4 years doing, is working these kinds of things out. And that, at least in this universe, is absolute hot. Okay? Now, I know we're going to have a Q&A session after this, so, but I want to answer one question that I know someone's going to ask, because I've been asked over and over again, and frankly, I've asked myself this over and over again. Why did I do this book? I thought it would be easy. I really thought it would be easy. And it wasn't. So, but there actually is a reason why I wrote this book. I wrote this book, and again, it goes back to the psychoanalyst thing. It all started in my childhood, literally started in my childhood. In elementary school, I had this wonderful elementary teacher, Don Lane, and this movie had just come out. Ray and Charles Eames did this movie called The Powers of 10. Some of you may have seen this movie, The Powers of 10. If you haven't, go find it on YouTube. It's wonderful. It's 10 minutes long or something. And it's a very simple movie, and he played this movie for us in class, and, well, basic conceit. Here's the concept. You start with 1 square meter, and they demonstrate this by this couple sitting on a picnic blanket in Chicago, and it's about 1 square meter on this blanket. And then add a 0. So let's go to 10 square meters, and then 100 square meters, and then 1,000 square meters. Just pull back. Let's see what it looks like if you just pull back by adding a power of 10. In other words, add 1 more 0. So there's 100 meters. I'm jumping faster than the movie. But go back to 100,000 meters. Go back and you start seeing, okay, here's Earth. And then you move back and you see the solar system. And then you move back and then you see our galaxy. And then you move back and you get the idea. You start to get a sense of how big is the universe. And then, brilliant move, they turn the whole thing backward and they zoom all the way back in, and you start going down by powers of 10. So from 1 square meter to a decimeter to a centimeter to a millimeter, and pretty soon you're looking at this guy's skin, and then you're going inside the guy's skin into the blood cells. Here's red and white blood cells, and then you go deeper and deeper until you see DNA, and then molecules, DNA molecules, and then into the atoms, and so on. And you got to understand, I'm this 12-year-old sitting there in class, mind blown. Like, what? And you got to understand, so ever since then, I've had this little niggling thought that's been bothering me. Ever since childhood, I've had this thought that really kind of tweaks me, that the vast majority of our universe is invisible to us. We generally have no idea what's going on. And even when you do find out what's going on, it's too much for our puny little human brains to wrap our heads around. So that's what I'm really trying to do with spectrums, is trying to go down, up, sideways, hot, cold, fast, slow, and see if we can wrap our heads around this even a little bit, stretch our minds even a little bit. So also as a child, probably teenage years, I started learning things about light and physics, and I learned that light, we pride ourselves in this ability to see a glorious range of colors. Just reds and blues, and it's incredible art and so on. But it turns out that what we see, visible light, visible color, is this tiny, unbelievably small slice of a much larger spectrum called the electromagnetic spectrum, right? And so we see this little bit of color, but it's the same thing. Technically, it's the same thing as radio waves, microwaves, X-rays, ultraviolet, infrared, gamma rays. All of these things are electromagnetic radiation, and we see this little piece because we happen to have these organs called our eyes that just happen to sense that little tiny segment. Like, I can't even tell you how small of a segment it is across the whole electromagnetic radiation spectrum. Little tiny spectrum. So I started wondering, what would it be like if we could see more? What would it be like if you could see, let's say you're driving down the street, and you look up and you're listening to music on your radio, and you look up and you see this mountain, and there's this huge, blindingly bright light up on the mountain, and you're like, that's the music I'm listening to, right? Because that's what radio is. Radio is sound converted to light, converted back into sound in your car. And those radio towers up on the hills, those radio towers are light bulbs. Technically, they're light bulbs, and they're putting light out all over the place. So that's cool. I think that's cool. So why is it? Why can't we see more of that stuff? Wouldn't that be interesting to see the music flowing? I think that'd be great. Now, there's actually a very good reason why we can't see those things, and that is because it has not been evolutionarily advantageous for us to see those things, right? Because visible light has an interesting quality that it bounces off stuff that's about our size. A mountain, a book, a person. It bounces off those things, and so we can see them. Radio waves, not so much. X-rays, kind of, but not so much. So it would not help us to be able to see radio waves because we'd be forever walking off cliffs, right? Because you couldn't see where the edge is. But because we see visible light and not the other stuff, we can actually make sense of the world around us at this general size. So that's kind of an interesting idea. Oh, another wacky fact. Got to go off on the wacky fact tangent. The reason we see color, by the way, is because most humans have 3 kinds of cone cells in the retina along the back of their eyes, our eyes, right? Colorblind people, some of you may be colorblind people tend to be missing one of those 3 kinds of cones. Each cone picks up a slightly different spectrum of sensitivity of light color, of frequencies. So colorblind people tend to be missing one of those, and so they see a reduced spectrum of color. It's very, very rare for people to not be able to see any color. They usually can see just a reduced amount. Now, what's trippy is that there are some people, primarily women, who have developed a mutant 4th kind of cone. They're called tetrachromats. And tetrachromats, we're trichromats, most of us, and tetrachromats can see more color. Or maybe they see more, they distinguish more variations of color or something, but they are among us. Now, why would that be important? Why would it be important? Why would that be useful for so many people to have developed this mutant gene? Well, one possibility is, let's say you're a parent, and you have kids, and the kids get a little sick, and they start getting a fever. It might be really useful, this is just, people don't really know, but it might be really useful if you could start seeing a feverish complexion. Because most of these people tend to see more distinctions in the reds and yellows just like in skin. They may even see, this has not been proven, but they may even see a little bit into the infrared. So they may be able to see literally when their child has a fever because they're getting warmer. They could actually see that. That would be cool. Now, so that's a little bit interesting in terms of an evolutionary advantage, but there's other times, there are other things that would be a huge evolutionary advantage. So, for example, let's say you're out hunting. You're in the forest, and a deer steps on a stick behind you. Now, what would be really cool is if you were like a spider on a web, and the webs, those strings of web would go out in all directions, and you could actually feel a tug. You could actually feel when that stick breaks. That's what sound is. Sound is actually a feeling sensation. It's our body's way of extending our sense of feeling out into the world. That's what's going on with sound, because when that when that stick breaks, the energy from that pushes some air molecules, pop, and those push some other molecules, and those push some other molecules, and it becomes like a game of billiards, where all those little billiard balls are knocking into each other all the way from there to your ear. And in your ear, we sense that little movement of the air molecules, just moving a little bit. And our ears are so sensitive that we can hear when the molecules move 1/10 their diameter, which is smaller than an atom. We can actually hear, now you don't hear it if you just get one of them, right? What you hear is the general vibrations, waves of energy as they get more dense and less dense. They compress and rarefy, right? Thicker, less thick. So this is, it's kind of like standing in a pond. You know, if you think of air as being like water, it is semi-viscous liquid, right? In some ways. If you think of yourself as standing in water and you're actually feeling the waves ripple over you, these little ripples just waving, and you can feel them compressing and letting go, and compressing and letting go. And that's what we hear, that's what we experience when we talk about sound. Now, normally you don't see sound, you feel it. It's actually moving stuff. But if you had like a big glass pane, and it was a really loud sound, you'd see it shake, right? So if you look at the shaking of an object and you look at the vibrations, you could actually get a visual of what sound is like. And that is actually what scientists are doing now when they're looking at the sun. Back to the sun. They look at the sun and they can see, I mean, the sun is this huge, roaring fireball in space, right? It's loud. But we can't hear it because there's an enormous amount of vacuum between us. So we can't hear it. But if you look at the surface of the sun and you look at the vibrations, you can turn that into sound and listen to what's going on in there. If you go farther, beyond our solar system, you can hear even more. Let me just do a quick reading from spectrums here. Talk about the lowest sounds. The lowest sounds ever found, far below the infrasonic thunder of animals, avalanches, or earthquakes, measured at even less than 1 hertz, are those of distant cosmic events. Now, many galaxies contain a huge quantity of free-floating gas, the residue of untold numbers of stars that have grown and exploded over billions of years. Astronomers, looking at a black hole in the Perseus cluster of galaxies, about 250 million light years away, recently noticed a pattern in the clouds. More dense in some areas, less dense in others. And the pattern soon revealed itself to be a sound wave emanating from the black hole. Now, the sound is a single note drawn out not over meters, but over billions of meters. And to be precise, the researchers have determined that it's a B flat, 57 octaves below middle C. 1,000,000 billion times lower than the lowest sound we can hear. And if you can imagine where a 20 hertz sound wave, 20 hertz is the lowest sound that humans can typically hear, a 20 hertz sound wave would take 1/20th of a second to pass by. A single wave of the Perseus black hole's drone would take 10 million years. Truly, the irony is palpable, for Plato noted that, quote, the empty vessel makes the loudest sound, unquote. So these are spectrums. They're spectrums of temperature, spectrums of size, of light, of sound. These are all objective spectrums. And you can measure them. We can all agree on them. There are all other less obvious spectrums that are still objective. Bobby Fischer will always be a better chess player, even in his death. I will never be as good a chess player as him, right? That is an objective spectrum of talent. There's lots of talent spectrums, and you can move up and down them, but there's a very clear objective spectrum there. Bobby Fischer's sister was even my 8th grade chess coach, and I'm still never going to be as good as that. On the other hand, there are lots of spectrums that are not objective. They're more aesthetic, so they're subjective spectrums. And I like thinking about this because it helps us get a grasp on just the idea of spectrums themselves. Subjective spectrums are obviously based on who's talking, when they're talking. For example, how much do you like vanilla ice cream? A lot? A little? Is it a 3? Is it an 8? 8.6? Right? You can kind of tweak that, and it's going to change over time, and it's obviously going to change from person to person. How angry are you? No one's ever angry or not angry, right? This is a spectrum. You've got... It's always a spectrum. As a writer, I love these kind of words, right? So I'm grouchy, which is less than cranky. It's definitely more than huffy, but that's a spectrum. Right? So... different people, now the key, interesting thing about these subjective spectrums is different people are going to be sensitive to different spectrums. We all have the experience of, maybe your spouse is more sensitive to heat than you are, or maybe more sensitive to driving fast than the other. There's all these subjective spectrums. Here's a good one. Graphic designers, as you heard, I have a background in design and publishing. And graphic designers are going to look at this and go, because they're sensitive. They've been trained to be sensitive to things like spacing between letters. And they freak, right? This is something you can learn how to do. They want to make it better. They want to come to some, right? So that's a sensitivity. Photographers can see things, they look at an image and they see, this should be 1 or 2% less red. And I'm like, you can't see that. But they do see it. It's really easy for me to discount it, but they see it, and that's why they're photographers and I'm a writer, right? So you get sensitive to certain things, and it's always on a spectrum. Now, for most of human history, we just had no idea that there was more than black and white, honestly. I mean, there was a sense of the world as being black and white. And for me, the joy of learning about the universe is being able to find these spectrums and then being able to name them, put numbers on them, right? Whether you're talking about ice dancing or you're talking about temperatures or whatever, the ability to know that there is a difference between 4, which is maybe okay, and 6, which is good, and 8, which is awesome, and so on. The ability to see the spectrum and name it is the joy of creating a greater appreciation of the world around us. Now, 130 years ago, we had no idea. We were just learning that there's these little tiny things, these little microbes that can't see without instruments that could make us sick. Who knew, right? 100 years ago, we did not know there were any galaxies in the universe beyond our own. Just didn't know. Now what? Now where are we? Now we point ourselves to the heavens and we see nothing but amazing, amazing things. Look at this dot. Isn't that amazing? Okay, that's not the amazing part. The amazing part is the Hubble telescope in space, or the Hubble Space Telescope, took a look at a little piece, a little dot in space. They weren't looking at that. They were looking at this little dot no larger than a pencil point in the sky. And what did they find? A lot. A lot. Now, these aren't stars, right? Those are galaxies, each of which have billions of stars. Let's go deeper and deeper. Because when you really look at everything, you cannot help but be amazed. There are mysteries and wonder everywhere. So our universe is big, right? Big universe? How big? Well, let's look at just our galaxy, big galaxy. If our galaxy, the Milky Way galaxy, were shrunk down to the size of a football field, then our solar system, our sun, and all the planets around it would be smaller than a grain of sand. So we're pretty small, right? But turn it around. We all know that atoms are tiny, right? But how tiny? Well, each of us, our bodies have trillions of cells in them, something on the order of 50 million cells. And each of those cells has billions of atoms. There are cells in your body that have more atoms in them than all the stars in the Milky Way galaxy. One cell. So, are we then unbelievably huge, or are we indescribably puny? Which is it, right? I like to think of it this way. Let me just read one more short reading from Spectrums. Now, we see a rose. We see a rose, and we attempt to understand its roseness by breaking it down, cell by cell, molecule by molecule, atom by atom, to its essence. And we discover that it is miraculously constructed from stardust, the remnants of supernova billions of years ago. And not only is it the same stuff that we are made of, we find that at a certain level, at a certain atomic level, it is truly difficult to determine where it stops and we begin. But as we draw our vision back, enhanced by our newfound insights, we find an even more astonishing perspective. The elegance of a single rose is different from the beauty and magnificence of a rose garden of 10,000 bushes. Neither is more beautiful, neither is more real. Both must be taken as part of the whole, and yet wonderfully separate. So it is in our lives, caught here in this middle world between large and small, cold and hot, slow and fast. We seem insignificant, less than a speck on a speck, and still hardly able to see, much less manage, the world of the atom or that of the universe. But appearances can deceive. Is a star any more important than we are because of its great size or power? A loud sound can demand our attention, but does it necessarily convey any more than a soft one? We humans have something neither the cosmos nor the atom has: mind. We can appraise and appreciate. We are curious and cunning. We delve and we dream. And who is to say that in the grand scheme of things, whatever collection of dimensions and multiverses we truly live in, that these qualities of mind are not just as meaningful as mass or momentum? I love this Dorothy Parker quote. The cure for boredom is curiosity. There is no cure for curiosity. So in Spectrums, I invite you to be curious and consider everything. Thank you. Thank you. We're going to